Hi everybody, welcome to Circuits, and we are going to start with Ohm's Law. This is 4.1. If you have access to the Coletta textbook, please go to 18-2, Chapter 19 and Chapter 20. Those will be the readings. If you're using OpenStax, 19.6, 20, page 20 and 21, if you're using the college physics of OpenStax. If you're using the university physics of OpenStax, that'll be Chapter 8, Chapter 9, and Chapter 10 of University Physics 2. So the homework, in Sapling, we're going to be doing the homework on circuits if you're in 112. If you're in 131, then we'll be doing homework 7 on circuits. And this will be related to labs 7 and 8. All right. So let's talk about what is an actual battery. And a battery is what gives something potential. It gives electrons potential energy. And that those electrons having now potential energy, that potential energy gets converted to kinetic energy and gets the electrons moving. So in a way, what a battery does is it raises up the height of the water or the electrons, and the electrons, being the water, will then take that potential energy and begin converting it into kinetic energy, which then lets them flow downhill. And then so this water wheel system could be considered almost like a resistor, and that gets converted to heat, or gets converted to another type of energy like heat and light. Right? So a battery in a way creates potential energy, and resistors consume that potential energy. All right? So what is voltage? If you're in 131, it is an electromotive force, also known as EMF. It's got this epsilon figure right here. So despite its name, electromotive force is not a force at all. It's referring to the potential energy, electric potential. So the voltage. The amount of work it takes to move an electron, to move a charge from one terminal to another, will be Q delta V, which we learned back in the voltage chapter. What is electric current? Well, simply stated, it's the change in charge over a period of time. So if you were standing there, you would be looking at the difference in charge flying past your eyes and count over a period of time. And so the unit of electric current is amperes, which is a capital A, and it is coulombs per second. So it's basically the amount of charge flowing past a point over a given period of time. Interesting enough, electrons are moving counter to the direction of the current. Okay, so I'm going to go ahead and click on this little button right here, and it's hyperlinked to PHET circuits. So I'm going to go ahead and create. I'm going to go ahead and create a mini circuit to illustrate this point. So here we go. I'm going to click on Intro, and here we have the area in PHET for the simulation. I'm going to drag a battery out. Okay. And I'm going to grab a little resistor or a light bulb. And I'm going to grab some wires, and I'm going to start creating this circuit. Okay. So notice a few things here as I create this circuit. Notice that it already has electrons in the actual wire. Okay. So that's one thing. So batteries don't create electrons it creates a voltage drop, which gets the electrons that already exist in the wire to begin to move. So a lot of people believe that electrons are basically power plants and batteries create electrons. They don't. What they do is they create a potential energy, which gets the electrons that already exist in the wires. It gives them a potential energy, and it gives, and they have that potential energy then gets converted to kinetic energy, and they begin to move. So I'm going to go ahead and go down here and connect this up. Whoops, I'm going to show values, and I am going to change this value to 3 volts. Okay, there we go. And I'm going to go ahead and change this guy to 9 ohms. Actually, let's go ahead and reverse that. Change this to 3 ohms. I like whole numbers. And we'll go ahead and change this to 9 ohms. And I'll show you the reason why I did that in a second. So what I'm going to do is I'm going to go ahead and connect this up. So notice that the electrons, if this is the terminal, let me go to the circuit board. On this is the negative side of the battery, and this is the positive side of the battery. If I go to the battery, notice that this is, let me break this for a second. Yeah, I'm going to go ahead and break it so there's no potential drop. That means electrons aren't moving. So this is the positive side of the battery. This is the negative side of the battery. The electrons already exist in the wire. Okay, and notice that the electrons aren't moving from positive to negative. Electrons will always move upstream. They will move away from the negative terminal and move towards the positive terminal, is because the negative terminal is negative voltage, and electrons repel electrons. Over here you could think of this as having a bunch of positives right here, and electrons are attracted to the positives. So the electrons in the wire get pushed away from the negatives, then they get pulled towards the positives over here. When I connect this up, what you see is that the electrons are moving, what is this direction? That would be called clockwise. But that's not the direction of the current. This is the direction of, it's called the drift. It's the drift velocity of the electrons. If I go over here to conventional, which shows this is these arrows are showing the direction of the current, which is flowing counterclockwise. It's flowing from the positive to the negative. So it's almost like we put a positive charge here, and it's being repelled away from the positive terminal of the battery, and it's coming around, flowing through this this resistor or light bulb, and its kinetic energy is being converted to heat and light, and then the electrons keep moving, and then they come back to here. Okay. So moving back to our presentation, that is basically how electrons are moving counter to the direction that the current is flowing. Current is flowing in the same direction that a proton or a positive particle would flow. The electrons are flowing opposite that direction. Okay. Interesting thing enough, electrons are extremely slow moving. Okay. So electrons are in a wire. So here we have a wire, and the electrons are kind of bouncing around in here. Okay. So right here we have electrons. They're kind of bouncing around. They don't just flow in a straight line. And so the drift velocity of the electrons is very slow. On average, it's approximately 10 to the -4 meters, right? meters per second. So it is extremely slow. Let me go ahead and change that right now. I'm going to go ahead and change that to meters per second. There we go. And close this. So electrons are flowing extremely slow. They're flowing at basically 1/10,000th of a meter per second. 1/10,000th. That's you taking, it's not even a millimeter. Okay. So it's extremely slow. But current, which goes the opposite direction that the electrons are moving, current is kind of analogous to the electric field. So it's in the direction that the electric field is flowing, even though current is calculated as the charges per second. Okay, so it's kind of weird that way. Resistance is the other element that we have to talk about. So resistance is basically it's the amount of voltage per amp. Okay, so it's voltage per amp, and that is what 1 ohm is. So 1 ohm is a volt per amp. Okay, and so what is resistance? Well, it's something that slows down electrons. So when an electron gets into a resistor, they have to slow down. So their kinetic energy has to bleed off in terms of heat. Okay, and so during the time that they're in the resistor, and everything has resistance, they are going to, the little electrons are going to slow down, and that kinetic energy is going to be turned to heat and light. And so that's what a light bulb does. Okay. It is calculated. Resistance can also be calculated in terms of the resistor itself. It's the resistivity coefficient times the length of the resistor divided by the area of the resistor. So if the resistor had a large area, okay, if the area went up, the resistivity would go down, right, and then become more conductive. If the length of the wire goes up, the resistance in the wire is going to go up. And not only that, if the resistivity, the coefficient goes up, then the resistance is going to go up. Okay, so different types of materials have different resistivity coefficients. Okay. Quartz has an extremely high resistance. It makes a really good insulator. It really slows down electrons to the point where they flow at an extremely slow rate, if not completely come to a stop. Okay. Well, the opposite is true for conductors. Okay. As you can see here, different types of metals. Different types of conductors, I should say, and they have an extremely low resistivity. So quartz 10 to the 17th resistivity, gold 10 to the negative 8th resistivity. And it's interesting, aluminum and gold have pretty similar abilities to conduct electricity. So copper, excellent conductor of resistance. So that's why you have a lot of copper wires everywhere. And copper is relatively easy to mine, so and plentiful. So that's the reason why we use it in a lot of our circuits, and not just gold. All right. Interesting. Also, another fact too is as objects begin to heat up, their resistance will also increase. When objects are cooled, when materials are cooled down, then their resistance goes down. Okay. There are a weird class of materials called superconductors where their resistance drops to 0. when they approach a very small temperature. So it's called a critical temperature. So as a wire, in all wires, as their electrons are flowing through them, they start to get warm, and then their resistance increases over time, and that causes them difficulty in conducting electricity. They're not going to heat up forever. They'll heat up to a temperature unless the current starts to flow extremely fast, unless there's a high amount of current going through that wire. So the temperature is analogous to the amount of current flowing through that object. So this gets us to Ohm's law. So Ohm's law is current is equal to voltage divided by a resistance. So these are the rules that we're going to be using right here to discuss circuits. Right? There are the three rules, but the main one right now what we're going to worry about is Ohm's law. Voltage equal to current times a resistance. That's a form of Ohm's law. But let's go to actually Ohm's law. So Ohm's law is a relationship between voltage, current, and resistance. Okay, and the way it's written is current is equal to the change in voltage over the resistance. Okay. So inside a circuit, there's this relationship between voltage, current, and resistance. It's interesting. Interesting fact is if resistance drops to zero, current is going to explode. It's gonna increase to infinity. Essentially, the wire will melt, and that's kind of what is called a short, where a fuse blows in your house, where if a house gets hit by a lightning bolt, those wires in your house can only carry so much current. So it may pop some circuits, and then if you're still hooked up to the power grid at that time, then the current will just explode in the house and melt certain components in your house. So it's interesting also too that you kind of need a resistance in order for this relationship to take place. There needs to be some type of resistivity in a circuit if you're going to have this relationship between voltage, current, and resistance. Okay? So let's try to go ahead and go through this and see if we could actually calculate. Let's use Ohm's law and go ahead and calculate resistance, current, and voltage in a wire. So what I'm going to do is let's go ahead and we're going to use the markup tool in PDF to look at this problem. So what we're supposed to do is find out the voltage across the resistor below, but what we also want to do is we want to figure out what the resistance and current is as well. So what we're given is that the battery is producing 9 volts, and it's also producing a current of 3 amps. And let's go ahead and let's calculate what this should be. And then let's go ahead and go to our simulation in PHET and confirm if we're right or wrong. Okay, so I'm going to go to a markup tool. So here I am in PDF Reader. I'm going to go to comments, and all PDF readers have the ability to do this. You go to comments right over here, you click it, and now this second menu pops up. Okay, and on the second menu is the ability to draw a text box, to actually use a drawing tool to erase anything that you've done, and also shapes. And here you could draw little vectors, create little lines, things like that. So let's go ahead and actually identify the direction that the current is going to flow. So let's go ahead and identify the direction that the current is going to flow. So I'm going to go here to the Shapes tool. I'm going to grab an arrow. It's red. I'm actually going to draw a vector right here, and I'm going to make sure that that guy is red. And make sure his borders are red. All right. So the reason why I grabbed that little line is because current is going to flow, like we learned from the simulation, that current is going to flow from the positive end of the battery through the resistor and flow back in to the bottom end of the battery. So current flows from positive to negative. So the amount of current that leaves is going to be the amount of current that's going back into the bottom end of the battery, because we saw that too in the simulation. I can draw these off to the side so we can actually see the current. And they said that this is a current of 3 amps. Okay, so that means the current is going to leave. It's going to flow to the right. It's going to then flow down across the resistor. All of the current is going to flow through the resistor. And then it's going to flow to the left across this wire, and then it's going to flow back in. So that's the direction of our current. Now, we talked about a little bit earlier that batteries create potential energy, and that resistors consume that potential energy. So 100% of the voltage that gets created by a battery gets consumed by the resistor. Okay, so that's a small little rule that we're going to talk about, but it's Kirchhoff's loop rule, which we'll learn a little bit later. But for right now, if this creates 9 volts, this resistor is going to consume 9 volts. So we know that for sure. So let me go ahead and draw that here. I'm going to go ahead and say, actually, I'm going to use the text box and draw that. So we know that the voltage that the resistor is going to be using is going to be consuming 9 volts. Let's make it look like the other stuff here. Whoa. There we go. So let's make this text box a little bit smaller so I could see the other things below it. And I'm going to move it. Here we go. So now we have the voltage that is being consumed by the resistor. Now we learned earlier that current, I could just use the text box tool. That current is equal to voltage divided by resistance. This is Ohm's law. Okay. What we could also write is that voltage is equal to current times resistance. And we could also say that resistance is equal to voltage divided by current. Okay, so we have all these little mathematical relationships that come right out of Ohm's law. Okay, so we have 9 volts being consumed here. by the resistor. We know 3 amps is flowing out, 3 amps is flowing across, 3 amps is flowing down through the resistor. So we know this has to be 3 amps. And so now, since resistance is equal to voltage divided by current, that we know that the voltage is 9 volts and the current is 3 amps, then we know that this has to be 3 ohms. Let's go ahead and check our program to see if it's doing that. So we have a 3 ohm resistor here. We have 9 volts being produced. Okay, I bet you if I'm going to go ahead and grab the ammeter, which is right here, and an ammeter measures current. So if I bet you that this is going to show 3 amps, because 3 amps times 3 ohms is equal to 9 volts. There you go. 3 amps is there in that wire. 3 amps is going up. 3 amps is going across the top wire. 3 amps is flowing through the resistor. 3 amps is flowing across the wire. 3 amps is moving down, and 3 amps is moving across. There's 3 amps across everything. All right. Let's move on to the next one. Can we figure out the voltage across the resistor below, but also the current leaving and the current going leaving the battery and the current going through the resistor? Well, we know this is 12 volts. And again, we know that I'm going to grab this from earlier, actually both of these from earlier, copy them here. So we know that if this is producing 12 volts, the battery's producing 12 volts, then the resistor has to consume 12 volts. So that's what we have there. And now we know this resistor is consuming 12 volts. This resistor has a resistance of 6 ohms. And what that means is 12 volts divided by 6 ohms is equal to 2 amps. So that is 2 amps right there. So 2 amps is flowing across the resistor. And what that also means is, since the 2 amps has to be everywhere, 2 amps has to be in this wire here, has to be across this wire and flowing back in, is that this battery is producing 2 amps. It's producing 12 volts, it's producing 2 amps. The resistor is consuming the 12 volts. Oops. And 2 amps is flowing through it. Well, let's test that again just to make sure. Our voltage is 12 volts, so our battery is 12 volts, and our resistor is 6 ohms. So I'm going to go ahead and change this to 6 ohms. Whoops, there we go. And change the battery to 12 volts. And hopefully this is going to show 2 amps. Yep. So 2 amps is leaving the top end of the battery, the positive terminal of the battery. Flowing 2 amps is continuing to flow there. 2 amps is flowing across this wire, flowing through the resistor, flowing across this other wire, flowing down, and flowing back in. All right. And so if you need to use the simulation, the link is here, but you could also click there on the picture. Another thing that we should talk about while we're here is power, the relationship of energy and power to electric circuits. So as we talked about before, potential electrical energy that we learned in the voltage chapter is equal to Q delta V. Well, power that we learned back in when we were talking about energy in physics 121 and 111. Power is work over time. And so work is delta U here. So that's joules per second. But work is delta Q, delta QV over delta T. So basically that is what a watt is. A watt is a joule per second. Okay. So this is 1 joule per second. And that's equal to 1 watt. And that's what power is. So when you look at a light bulb, it has a wattage, and that tells you how much energy it's using for every second. So power in relationship to circuits is current times voltage. Okay, and since you have Ohm's law here, which we could use right here. So I'm going to bring this right here. So if power is equal to current times voltage, and voltage is current times resistance, then current squared times resistance is power. Another way to write it is current power is current times voltage, but current is voltage divided by resistance. So voltage squared divided by resistance is equal to power. So power is equal to current times voltage, voltage squared divided by resistance, or current squared times resistance. And that's how to calculate the power of a resistor, or of a battery, or of your system. Okay. Again, the units of power that we typically use is a kilowatt hour, and a kilowatt hour is 1,000 watts. So if you look at your electric bill, they calculate things in kilowatt hours. So how many thousands of watts are you using for 3,600 seconds? Okay, and basically that is the amount of joules that you're using. So 1 kilowatt hour is 3.6 times 10 to the 6 joules of energy that you're using within that hour. Okay, so a resistor is consuming that voltage. Okay, and if you have a current, if you have a coulombs per second, which is your amperage, so this is 6 amps, and you have a voltage, which is a joule per coulomb, well, basically this is consuming, is producing 72 watts. Okay. You could find your power at the back of any appliance. So it tells you how much voltage it's consuming. It'll tell you how much voltage it's consuming. So this is a big object. It's probably like it must be some type of electronic equipment that's a recorder or something. Oh, yeah, it is right here. So it's consuming, it needs 120 volts to power it, and it's producing 18 watts of energy. Okay. Well, it needs 18 watts of energy to run it. Okay. So different objects have a different power need. So here, air conditioners consume a lot of wattage produced, right? So they need a lot of current and voltage. Okay. So that is basically our intro to circuits. I hope you enjoyed it.